This slideshow will attempt to explain differential pressure drift due to tank pressure swings. It will start with differential pressure basics and end with a demonstration. A differential pressure gauge simply measures the difference in pressure of the top and bottom of the tank. The gauge displays this measurement in inches of water. The top of the tank's pressure is communicated to the outside of the tank using a small stainless steel line. It is called a low phase or LP line. The bottom of the tank's pressure is communicated using another stainless steel line called the high phase or HP line. The HP line is designed with a trap in sufficient length to minimize heat leak. The differential pressure measured by the gauge is the pressure difference from the top of the tank to the top of the liquid in the trap of the HP line. Inches of water column can be converted to tank volume or weight measurement based on product properties and tank geometry. It is typically displayed on the tank in the form of a lookup chart. The high phase line is insulated to promote heat into the trap to try to control the position of the liquid in the trap. Recent vintage tank designs and construction take great care in controlling the liquid position due to the industry's move toward telemetry systems. A cryogenic tank design is a tank within a tank similar to a thermos bottle. The space between the inner vessel and outer vessel is often called the annular space. This space is under vacuum, is insulated, and allows for process piping to have sufficient traps and lengths to minimize heat transfer into the liquid from the outside world. The gauge assembly includes a pressure gauge that measures the pressure of the top of the tank and a differential pressure gauge that measures the liquid column in the tank. Isolation valves are located at the penetrations of the outer vessel. These valves are used when servicing the gauge assembly. The equalization valve, when open, creates a bypass between the HP line and LP line, resulting in no differential condition. This can be used to check the zero of the differential gauge. The HP line design is key in making the differential pressure gauge read accurately. Over the years, the design of this line has changed due to insulation systems and the need for more accurate measurement. The graphic shows an HP line that has a 10-inch trap section with the bottom of the trap insulated and the majority of the trap section is exposed. This bare pipe section helps maintain the liquid height within this zone. This example has a measurement of 67.3 inches of argon above the liquid in the trap. Argon is about 17% heavier than water, and therefore the gauge reads 78.7 inches of water. Obviously, the gas in the top of the tank will add to the total differential pressure, but has been ignored in this example to simplify the explanation. The next series of slides will explain the differential pressure drift and the corresponding level drift due to a pressure swing. This drift will vary from tank to tank based on the tank's design, insulation system, and manufacturing tolerances. Very simply, as the level of the liquid in the high phase line rises, the liquid level indicated at the gauge drops. This is due to the gas space above the trap compressing during tank pressure rise. The opposite is also true. The indicated tank level will rise during a pressure drop in the tank. For the following example, the tank has seen heavy use during the day and is at 210 psi gauge pressure. Heavy usage and sometimes normal usage can result in a tank without subcool. This means the liquid in the tank is in a light boiling mode. By the nature of heavy or normal usage, the liquid in the high phase line will be toward the bottom of the trap. In this example, the differential pressure gauge is indicating 78.7 inches of water. As described in the previous slide, the tank ended the day in a light boiling mode. During the non-usage, the tank's pressure will rise until the liquid has resaturated, and the tank pressure has risen to that saturation pressure. In this example, the tank pressure rose to 235 psi gauge pressure. 210 psig to 235 psig is approximately a 10% change in pressure. With a 75-inch gas space above the liquid in the high phase line, due to ideal gas laws means the liquid in the trap will move 7.5 inches. The slope of the high phase line results in a 2.5-inch vertical change. 2.5 inches of argon is equal to 2.9 inches of water, resulting in a new gauge reading of 75.8 inches of water. As mentioned, the swings in level or drift can be calculated. The calculation is based on the ideal gas law. This slide highlights the compressible gas section of the high phase line. For our calculation, this length will be known as L. The ideal gas law states the amount of gas is determined by its pressure, volume, and temperature. That determination is represented with the equation PV equals nRT. We can use this relationship to determine the change in compressible gas space in the high phase line. In our example, N, R, and T are constant. Therefore, the starting condition and ending condition must follow the following. P1 times V1 must equal P2 times V2. We know the starting and ending pressures, and the volume can be related to the length of the phase line. To recap, the starting conditions, or in our case the end of the day, we had a tank pressure of 210 psig and an indicated level of 78.7 inches of water. The ending condition, or the start of the day, the pressure rose to 235 psig and the level dropped to 75.8 inches of water. This drop was due to the level rising in the high phase line, trap 2.5 inches. We mocked up a test fixture in the lab to demonstrate the drift due to compressing the gas space in the high phase line. Our mock-up used a high phase line to scale based on a 1990 vintage tank. The fluid was water with blue food coloring.